it's very interesting. It's the first time we're moving away from the computers we've used for getting close to a century. And so I think it is a very interesting revolution in a way. And if you are a pragmatic person, I think you realize that, you might worry, you might not worry, but things happen. Like either you do it or someone else does it, and it's gonna keep happening. And so the only view you can take is pragmatic and be prepared.
Yeah. Second day of PRP in Riga, and with us is Benjamín Villalonga, or Benjamín.
No, great pronunciation in Spanish.
And Benjamín works at Google Quantum AI.
Yeah.
Based in Santa Monica, California.
In Los Angeles, in Venice.
Los Angeles.
Right by Santa Monica.
And he's a research scientist there and works on classical simulations of quantum systems.
Correct.
And is primarily focusing on benchmarking and NISQ devices on quantum error correction. But fill in the blanks.
Yeah. So most of the work I've done in the team, well, my PhD background is in condensed matter physics, in particular on classical simulation techniques to understand, physical models of quantum matter, phase transitions, things like that. And it turns out that the tools you use in that field are actually very similar to tools that are very useful in quantum information and quantum computation from the numeric side, from the classical simulation side. One tool that really stands out in that field is tensor networks, which is a mathematical tool that has applications in many fields, but in particular it was developed a lot in physics, in condensed matter physics. And that's something I use a lot nowadays. So I've been in Google for a bit more than 5 years. And in those years, I've worked quite a bit on NISQ experiments, where NISQ stands for noisy intermediate scale quantum devices. And so the first major experiment that was run in this regime is something that maybe sounds familiar, called RCS, or random circuit sampling, which was a very interesting setup because it was the first time that it was a serious attempt to try to do something beyond classical. So what at the time we called, or it was already called, quantum supremacy. So we prefer to use the term beyond classical now, and it's very explicit. It's performing some task on the still noisy, still small quantum computer that seems to be really hard, and with some actually theoretical guarantees that will be very hard to replicate with classical means, with a supercomputer, for example.
Yeah.
And so for many years, we've repeated these experiments in bigger and bigger platforms, and now it's very well understood from my side, from the classical numeric side, and with, in particular, tensor networks as a very good tool to simulate small quantum experiments, that it is really beyond the reach of classical methods. I think our latest estimates are like, you're getting close to a billion years on the biggest supercomputer on Earth if you want to really replicate what we run in a few minutes in the lab. So that's one thing I've devoted a lot of time to. Now I'm working also on other NISQ experiments with a bigger application flavor. Not only random circuit sampling, which is a very niche, not even an application, it's just some well-defined problem that we can run, but really doesn't have any utility in mind.
And maybe to dive into, how did you end up at Google Quantum AI? What was your training, your formal training?
Yeah. So I studied undergrad. I studied physics in Spain, and then I came to the US to do grad school, to study a PhD in physics. And I happened to land in a team where my advisor had a strong background. Also, he had worked in quantum information in the past. And
did you always want to do quantum, or was it more by chance?
No, I actually, during undergrad, I had a course in quantum computing that I loved. And so it's something I had in mind. I think there has been a lot of investment in the last few years, so now the field grew a lot.
Now it's growing now, but back then probably.
But at the time I was really collaborating with professors, doing research in condensed matter, and that's something I also wanted to do. So I started my PhD there, but when I was in the PhD, I saw the quantum information community kind of start growing and start getting a lot of funding, and it sounded like a really cool time to work on those problems. So mid-PhD, I started collaborating with the team at NASA that does quantum computing. And And then I ended up working on this random circuit sampling experiment because they were collaborating with Google. I also spent some time at Google. And finishing my PhD, I collaborated still with both of them. And when I finished, it was kind of natural to go down that path. And I ended up having a full-time position at Google.
And how was the experience at NASA, if I ask?
Very nice, very, very interesting, right? Like it's a unique place. So they have a very strong theory quantum computing team, and they collaborated with many other institutions. But at the same time, while you are working there, you see, I don't know, things that you've only seen on TV, right? Like someone working on the Mars rover, or someone working on devices that are going to go on the space shuttles, etc. So it's very interesting people that you meet there, for sure.
Yeah, I would say that the tasks are also probably unique to this place on Earth.
The tasks?
Yeah, I mean, maybe that's the only institution you will work with the Mars rover, probably, in the world.
Right. Or, well, definitely all the countries have space agencies, or Europe also, but definitely it's an iconic one.
Yeah. So maybe zooming in into Google Quantum AI or Google Quantum, for the non-informed viewer or anyone who wants to learn just the gist of it, to get the gist of it, maybe you can walk us through Google Quantum AI stack from the hardware, quantum hardware, classical hardware, anything in between that, to the optimization algorithms, and maybe also the application layer.
Yeah. So the team's main focus is to have useful quantum computation working, in a few years. And so the biggest part of the effort is to actually have a quantum computer working first, right? And at the same time, we're developing applications so that we can run interesting applications and solve interesting problems by the time the quantum computer is working very well. So there's a large hardware team. In particular, there's different proposals for how to implement a quantum computer. We work with superconducting qubits that are, this is some material where you print superconducting qubits. Yeah. And then you have some very complicated control electronics and wires coming into this chip. And this is all.
That's the famous image of the.
Yeah, the famous picture of the dilution refrigerator. That is the gigantic thing, but at the end of the device, there is this little chip that has all the qubits. And all that is doing is lowering the temperature.
And the chip is called Willow, correct?
Willow is the best chip we have currently, yes. And so the hardware team is constantly improving the device, and every now and then we announce a new device that is larger, has better error rates or lower error rates. And so, but there's something that there's a fundamental blocker in keep going with this process, having more qubits and having lower error rates. And what happens is that it's really hard to have the error rates be as low as you need for big applications of quantum computing. And so there's this layer on top called quantum error correction, which relies on some theorems from the late 90s and early 2000s work, and then improvements over that, that promises that with some overhead in qubit count, you can really encode logical qubits where you're going to run your applications that have drastically lower error rates.
So logical qubits are lower in error rate than physical qubits.
Yes, yeah. We have already demonstrated in experiments that we can build a logical qubit that holds information with better error rates than any of the physical qubits we can fabricate.
All right.
So, meaning in technical terms that we're operating below threshold. The physical error rates are so low already that if you apply these ideas of quantum error correction, you can generate a logical qubit that operates at much lower error rates. And so the way to get to long-term applications goes through implementing quantum error correcting codes over many modules and many logical qubits. And so a big part of the team and really many of our milestones go down that path. We're trying to demonstrate error correction is possible in the large scale. But in the meantime, we have small-ish, we're beyond 100 qubits and with very good fidelities, very good error rates, but still smallish devices that have errors. And so with those devices, because they are very, very refined and much better than what you would imagine a few years ago, we can already do experiments, right? And these are so-called NISQ experiments. So there's no error correction over them. There's some techniques to try to mitigate errors, so-called error mitigation techniques, and we apply them every time we run an experiment. And so experiments you can run nowadays, and we have published a lot of these, are typically experiments that are simulating physics. So what happens on a physical model that is trying to imitate something that happens in nature, but really taking away all the complicated elements. Like, so you design some simple model of some effect, and you encode it in a small lattice of, say, 100 qubits. 60 qubits, 70 qubits, 100 qubits. And you can simulate this, or you can run this on the quantum computer. It's not protected, meaning errors are there, but you can still read a signal, and you can mitigate the errors and read a stronger signal that might answer some interesting physical question. And these NISQ experiments are going to slowly transform into long-term applications as error correction start becoming a more and more common reality.
And what would you say from this whole layer is the rate limiting step? Where is the most work focused on? Where do we have the biggest challenge right now?
I see. So I'm not an expert in hardware, but from what I understand, it is challenging. Different platforms have different challenges. Some of these challenges have to do actually with the control. Like, it's very easy, I understand, to print more and more qubits. You could have a device with 2,000 qubits if you want, but it's kind of unusable because there's not enough space to have so many cables come into the chip and control such a large device. There's calibration efforts. Once you have a device, you have to decide exactly what frequency each qubit is gonna operate, how they talk to each other, how you apply logical gates between them, etc. And so getting all of these numbers right, all of the calibration right, is very complex. You have to solve a lot of engineering problems to get that working. And so the larger this gets, the more confident you want to be in the techniques you're using to really understand what errors are happening, how to improve your control, to have lower error rates, and this over a larger and larger scale.
And would you say it's a time constraint? Like with more time, we will just get more qubits?
Well,
the more we calculate, or is it capped to a specific number?
To a specific
number, let's say 10,000 qubits, and we don't have a solution beyond that.
I don't think we're close to any fundamental. From my understanding, we're not close to any fundamental blocker.
Yeah.
But there is this continuous progress in getting things better and better. Now, the nice thing is that as you improve a little bit your error rates, because we're working below threshold, error correction guarantees that once you implement this whole layer of error correction, error rates will drop dramatically, exponentially fast. As you increase, as you improve your error rates a little bit, and then you increase the size of your logical qubits a little bit, then the error rates drop exponentially fast. And so in the next few years, we're going to see very quick progress in that regard.
Now, so the next is it exponential growth or
exponential growth in the number of qubits? I don't know. I haven't seen the the historical data.
Yeah.
But I would say so. Like, not long ago we were working with 10 qubits, 20 qubits. Then 2019 we had an experiment on more than 50 qubits. Now we have a device with 100 qubits. The next milestones will need a few hundreds. So it is accelerating for sure. Yeah.
All right. And how does a classical computer play into the everyday quantum hardware in today's framework? How important is it? How often do you use classical computers in your job, let's say? How can someone imagine the usage of a classical computer together with a quantum computer?
So in many, many ways. So I'm going to start from things that are further from my work and then things closer. So definitely classical computers are the ones managing the whole control of the quantum computer. So it is relying on on very quick, very fast classical computers managing the whole system. Also, if you want to run something on the computer, you are not doing it with your hands, right? Like you're sending signals with some quantum circuit. You develop some quantum circuit you want to run. You do this in Python. This gets compiled to some signals that are going to be sent to the qubits. Then you press a button, and that runs. You collect data. There's a lot of classical computation involved in all of that. Now, in the design of of the qubits and of the whole device, there's a lot of classical simulations of what is happening, right? Like you have an understanding of the physics that are happening around your superconducting qubits, and you try to model that as accurately as possible and simulate that as accurately as possible. And we have classical techniques to do this. They don't scale well, because if they did, we would just simulate a quantum computer, and we would, have a quantum computer simulated by classical computers. So they're not supposed to scale well, but they scale as much as you can to have the best understanding you can of the physics happening and try to have better designs, reduce errors, etc. Once you abstract the layer of physics, you can try to simulate what is happening to the information. Well, what is the computation that is happening in the quantum computer? And that's something closer to my work. So when you run an experiment, you want to verify that it's doing the right thing. And so for smaller sizes that you can simulate, you can really cross-check that you're getting the right signal. Beyond this classical regime, you can try to argue that classical methods could get better, right? And you can fight any claim of some beyond classical computation. And so that's also close to my work. We try to improve existing classical methods to simulate quantum computations, or invent new ones, or enhance existing methods to do as good a job as possible to try to fight any beyond classical claim. And sometimes that's very interesting because it informs future experiments of where you can really develop an algorithm, in what region of problems you can develop an algorithm that is classical, it's efficient, or at least it's doable to run on a supercomputer. And maybe there's not a good idea to try to find some quantum application, but at the same time you learn where it's really hard and what the pocket of possible very nice beyond classical applications might be. Another thing, and that's interesting work actually I presented here about this, is that we can use classical techniques to predict guarantees for the performance of some quantum algorithms, right? So we have this not NISC, but actually long-term vision of what algorithms will do, or what kind of algorithms we'll be able to run. And for this is a prediction, right? We don't have good enough hardware to run all of these algorithms yet. And so how do you know?
Are these new algorithms, or are these older algorithms?
Well, both. There is always work every year. There is progress in getting new algorithms or variants of existing algorithms to solve new problems, but there's also a whole plethora of existing algorithms for different applications. In particular, I did some work on this optimization algorithm called the QAOA, which for a long time was considered very heuristic, like something people would try in a small simulation and see if it works or not. But now we have methods to predict its performance in very large instance sizes. In this case, in our work, we analyzed what happens when this algorithm is applied to a graph, this for some graph problem, to a graph in the limit of infinite size. And so this is clearly beyond any simulation. And so we have classical methods that require classical numerics to guarantee performance of how well this algorithm will do when we are able to run it on gigantic instances. This involves tensor networks. And so the nice thing is that without simulation, but with a classical computation of a different kind, you can predict what an algorithm will do. So this is another use of classical methods to inform your decisions and to enhance your progress in getting to useful applications for quantum computers. And finally, another application of classical computers in quantum computation is decoding. So these error correcting codes that eventually all quantum computers will be error corrected, so that you get error rates that are so small you don't have to consider them, or they are not too obstructive to your algorithm.
Is this also called noise reduction in some ways or not?
No, it's different from noise mitigation.
Okay.
So noise mitigation, with noise mitigation, you're trying to enhance a signal from some computation you are running on some device with noise, with a lot of noise.
Okay.
With error correction, you're really trying to get rid of noise as much as possible. So you can think of the quantum computer as completely clean. It's going to exactly run the circuit you want with no error happens. To do that, one critical part of the whole protocol of error correction is decoding. So it's measuring some pieces of information in the system. You want to have a guess of what errors happened, so you can correct them or at least keep them in mind. And this loop where you extract or you try to predict what or to guess what errors happened, and then you take some informed decision with that, either apply some operation or keep that in mind for the end, is called decoding.
Got it.
And decoding is a very intensive classical task. And so developing better decoders and have better implementation of decoders that have to operate in very short timescales.
Okay, so just to double that what you said, you are not just building a quantum computer, you're basically also improving classical decoders and classical computers.
Yeah, to build a quantum computer.
It's a double challenge in a sense.
Correct. There is a lot of engineering problems around quantum computing, and many of them involve classical computer science. Yeah.
So anyone who is in computer science essentially can contribute meaningfully without maybe having like the full quantum information background.
Yeah, we actually hire a lot of people with different backgrounds that, maybe without any quantum information background. Particularly for decoding, we have people that worked in high frequency trading.
Yeah.
Right, so they are used to this very high, very small time frame feedback with very intensive classical computation, right?
And finally, those people are often physicists. And finally, these people are often physics.
Sometimes they are physicists, sometimes they are not. Yes, yeah. Or we have people coming from, I don't know, I believe we have someone coming from the aerospace industry, that are very good at shielding chips from radiation, and that's something we really have to take into account here. Yeah, there's different backgrounds that contribute.
So it's a multi-field domain to get to the next stage of computing, which would be quantum.
Yeah. The field transition from theoretical ideas to having some proof of principle implementations and experiments to now taking it in all its seriousness, where we realize, the community realizes that without solving very critical engineering problems.
So we stopped with the whole idea basically of the advancement, not just of quantum, but also classical. And I assume also maybe the advancements of the algorithms themselves and getting them better. One particular field which is in talks in a majority of use cases, especially from the business side, is the threat or the idea of Shor's algorithm or a similar optimized algorithm running on a quantum computer which is large enough could break RSA encryption. Or not just could, but very likely would.
It will.
Will probably. So just maybe some thoughts from you, and these can be your personal thoughts. What would you say to this problem statement, and what are your general thoughts to that?
Several, I guess. So this will probably happen. So it's something that people have to keep in mind, or decision-making people for critical areas.
And it's very important for national security.
It's very important for national security. That's what, in the first place, got a lot of interest in the 90s in the field. And so since this will happen, it's still not happening, not for some years. But I hear constantly that it's incredibly important to switch to quantum secure protocols of encryption.
And in the last few years, there was a big advancement in the algorithms which can protect against a quantum threat. NIST is recommending four proven, let's say, encryption schemes which can protect against a quantum attack.
Right.
And we have clarity on that, and therefore it's also a recommendation by the NIST to switch to quantum-resistant security until 2035.
Right. Still until we switch,
exactly.
All this information is probably being stored, and it'll be decrypted eventually.
That is happening right now.
You guys are experts in the field.
People are telling that, and we hear that often, that basically data is harnessed and basically stored, so it can be decrypted later.
Right. So it's not like there is kind of a deadline. It's a little, it's not clear when it's going to happen. when you really have to switch.
Yeah.
But the earlier the better. So,
The
so
earlier
there's
the
less
better.
harnessing of data that is
Exactly.
basically unencrypted.
And also, it's very important to decide which data to protect because some data is more valuable than the other data.
Right.
So it's not necessary to protect everything at once, but the very, very highly, let's say, protectable data, or the data which has to be protected a lot, should be quantum resistant, actually today already.
Right. And of course, we have some estimates of what kind of resources you'll need to break RSA, when a quantum computer will be able to do this. But these estimates keep getting better and better, meaning daily less and less resources. I think the record now comes from a paper from Craig Gibney from our team.
Yeah.
And he improved in many ways, many directions. And that decreased a lot the number of qubits you need, the number of operations you need, the error rates you need to fully break RSA 2048. So so it's definitely something that's present there, is looming over everybody. And so it is, there's many applications of quantum computation, and there will be more once we can play around with actual quantum computers. But this is one that is definitely coming, and it's important to take into consideration.
And it's one field we do know, because a lot of the things we just don't know, since we don't have quantum computers at industrial scale. So probably we'll see a lot more applications. But this one we definitely know is actually impactful.
Yeah, exactly.
All right. Maybe just to dive in more into your work at Google Quantum AI, and we talked a lot about MNISC. And have you ever looked into or touched base around fault-tolerant computers on the quantum side?
I have a little work, not on the error correction per se.
Yeah.
Well, I have done some work in decoding, but for algorithms in the fault-tolerant era, I have some work on optimization.
Yeah.
I mentioned part of that. So we've looked at what happens when you apply this optimization algorithm, the quantum approximate optimization algorithm, in some problems. And those problems for very large problem instances. And those seem very far removed in the future. Right? Like this applies to very large graphs. You need a fault-tolerant computer to
What's the timeline, just for us to understand, about fault-tolerant computers?
Fault-tolerant computers? Yeah. Well, I would like to think that we'll see something very close to that within a decade.
Yeah.
It's a
within this decade, or
within a decade.
Okay, so until 2036. Or not 2030.
Let's see, I'm not going to say a number. It's a research field, right? So you never know what's coming ahead. Like, we're solving one problem at a time.
Yeah.
In particular, we organize our research in milestones.
Yeah.
As far as developing the quantum computer is concerned.
But is this a milestone within your?
Yeah. The final milestone will be having a large enough quantum computer that can do things like, factoring to large prime numbers.
Okay.
Yes. So the next milestone, by the way, is going to be having a logical qubit. We've already demonstrated that we can have a surface code, which is the error correcting code we're using, the protocol we're using to protect data from noise. And the next milestone is going to be having a logical qubit that is very good, that has very low error rates, that starts having some lifetime that is measurable kind of by a human. It doesn't last less than a millisecond. It's actually something large. And once you have that, a lot of engineering is there already. Once you have that, you can have several of these, start making them talk to each other, have logical gates, and build little by little a large quantum computer.
So in a sense, there are some or a lot of activities lined up, and when we reach a specific hardware milestone, it will not just unlock one specific layer in a sense, but it will be definitely a measurable impact, because a lot of things are just waiting for the hardware to come along.
Yeah, it's not going to be a transition point, right? Like there's continuous progress, and in the meantime, there's always things to do with the new hardware.
Yeah.
And in particular, there's going to be this intermediate regime where you get some partial fault tolerance.
Yeah.
Maybe not the full fault tolerance that we dream of, where everything is completely protected.
Yeah.
But once you have low enough error rates for a lot of logical qubits, you can start doing a lot of things. You have access to many more operations because each one has a much lower error rate than we have right now on the fully unprotected NISC device. So progressively, we'll see more and more applications kind of unlocking, and in larger and larger regimes.
And we can also factor in that probably more developers will join by that time.
I think so, and the nice thing is that once you have a platform, so classical computers were developed with very few applications in mind, and now we use them for everything, the stupidest thing you can imagine.
Yeah.
And it's just a matter of trial and error, and we have a machine that is super reliable. You just try something, it works, you use it. There's a lot of heuristics. Machine learning now is in such an explosion, right, of applications, and it's all based on very heuristic methods that work very well.
Yeah.
And so once you have a quantum computer that starts approaching something fault-tolerant, you can experiment with it so much that we probably find so many applications that just work. And so right now, the job is very hard, right, for people that develop quantum algorithms, because you're trying to predict what's going to happen once you have a machine that you still don't have at the level you want. And so you need very refined math to maybe in some cases prove that you can do something or something else in very contrived problem settings. But once you can apply that to real problems, you can probably try a lot of ideas that now you would have no clue of, even start proving that they would work or not.
Yeah. I mean, one particular field is, for example, drug discovery in pharma, I would say.
Yeah.
Where you try to fit three-dimensional
molecules
to
materials, simulating molecules.
Yeah.
That's probably among the, maybe not at the large scale that you would need to simulate complex molecules, but definitely starting at some smaller scale is probably one of the first applications.
Yeah. And that has huge impact for our lives. I mean, most likely.
Eventually, yes.
Yeah.
Eventually, yes.
Yeah. So maybe also to explain why are tensor networks so important and what do they do in regard to a quantum computer? Because tensor networks, a lot of people most likely associate them highly with machine learning, since these tensor networks or TensorFlow specifically was the research lab which produced the Attention is All You Need white paper, which ultimately powers transformer technology. And in the quantum aspect, why are tensor networks also necessary?
Yeah, so tensor networks have also had less visibility, is more of a technical term, but it also has had an explosion in the last 15 years, 10, 15 years. They originally they were reinvented in many fields, but the field that has continuously used them for a long time is condensed matter physics, and they are very nice mathematical structures to capture quantum information at the physical level or at more abstract levels. Nowadays, you can use them for a lot of classical problems too, but they are naturally capturing very well quantum physics. So a tensor network is actually something very, very general, something universal. You can encode any computation on a tensor network. Is any classical circuit. Any classical computation you can run as a tensor network. Any quantum circuit you can run as a tensor network. It's a subclass of tensor networks. And actually, if you could there is this operation with tensor networks called contracting, which is kind of evaluating the tensor network. If you could evaluate or contract any tensor network efficiently, then you would solve problems that are called Sharpie hard. It's some very complicated class of problems, much bigger than even what quantum computers will be able to solve. And so there's this huge framework that captures a lot of problems in the abstract world of problems.
Yeah.
And so the problem is that they are not easy to contract or to evaluate. And so only in some cases they are. Now, since every quantum computation and every quantum circuit and every physical system that needs quantum mechanics, you can write down as a tensor network, as this mathematical language, then in the cases where you can actually evaluate them, they give you a lot of insight into that system. And so every time you look for some quantum advantage or something that is beyond classical, you don't want to be in that regime where a tensor network would do it. Now, before you get to that regime, tensor networks are very good tools. They're naturally encoding what's happening in your processes, in your quantum computation, in the device that is holding your qubits, etc. And so they're very natural tools to really get into many pocket areas of quantum information. In particular, simulation is a huge one. We use them to, as I was mentioning earlier, to simulate the physics happening in the device. We use them to simulate the computations happening in the device. We use them to see where the limits of classical methods are and try to go beyond that with a quantum device, or try to be below that limit to try to check that the quantum device is doing the right thing.
But tensor networks, they span over the boundaries of quantum and classical, correct?
Yeah. So they really, what people thought it was possible classically to simulate quantum physics and particular quantum computing.
Yeah.
Turns out that tensor networks expanded a little bit more.
Yeah.
They're still a classical tool, but they bought a little larger region.
Yeah.
And so they kind of corner quantum computers to, have beyond classical applications a little further. And so they're this expansive technique that kind of ate up a big chunk of what was thought to be not possible to do with classical computers.
And do you think the more the classical computers progress or improve, do you think the goalposts for a quantum computer are shifting then?
Yeah, that has always happened. So, in 2019 we put out a random circuit sampling experiment that we claimed was beyond classical, and eventually tensor network techniques improved so much. And these improvements they go exponentially fast when you haven't reached the limit, and then at some point they stop. And so they made that experiment simulable. And so we had to, in the later versions of the experiment, to grow the system and grow the depth of the circuits and basically the computational volume quite a bit to leave tensor network techniques behind. And so tensor networks, or all the methods in this latest experiment, the out-of-time order correlator, we call it quantum echoes experiment. Also, there were a lot of classical techniques that were kind of threatening different areas in which these autos seem to be beyond classical at first. And so we had to think very hard on how to be in a regime where we think no classical algorithm can get there. But of course, it's always open to a competition between quantum computers and classical computers.
Do you think classical will fail ultimately because of some complexity, or?
Yeah.
Or can we expand tensor networks infinitely?
No, not indefinitely, right? Humanity keeps exploring more and more techniques, and we haven't exhausted every idea. So of course, there's always chances that you get better, and empirically you find that every year techniques get better. But there is some points in this complexity class kind of map where we know classical computers should not get to, like based on conjectures that everybody believed to be true. Quantum computers will probably have an area that is never reached by classical computers.
So the ultimate case is always the same. So we need it. It's not negotiable.
To have a quantum computer, to develop a quantum computer, yes. Yeah, based on the vast majority of the scientific community believes, there is already, maybe we are testing the limits, but there is an area where only quantum computers will be able to solve stuff. And so the nice thing is that with this competition improves classical methods and then have applications elsewhere. So
that is interesting actually, because it pushes the boundary of classical, and then you can use this for something completely different.
And
does it happen?
Yeah, one example is tensor networks. Without these beyond classical claims from random circuit sampling, tensor networks they were being developed and improved because people in physics have used them for a couple of decades or more. But they took a big leap once the competition was out, and they improved a lot. And they are used in quantum chemistry, in condensed matter. They're used a lot
in machine learning.
In machine learning,
Could we claim that without the push for the boundaries of classical computing, even though it's an indirect contribution, but since it improves tensor networks and they are a crucial part of transformers technology for large language models, that this is still related, and this advancement of quantum and then classical also contributes to such a big field we see now, which is AI, obviously.
Yeah, I'm not an expert in machine learning, so I know high-level ideas, but I'm not sure the techniques that were used to simulate random circuit sampling, for example, or that are used in the quantum information community, helped develop large language models. I'm not sure if that progress directly influenced there.
I'm not saying it's a direct implication, but it could have pushed the boundaries of classical computers.
It did push the boundaries of classical computing, yes.
And without that, we don't know if it would happen.
And actually, at some point, we had actually the simulations we run at NASA, no, at Summit, at the Oak Ridge National Lab.
Yeah.
We ran some very intensive tensor network computations. For a while, and this was simulating quantum computation, quantum computers. For a while, we had the record on the flops per second that you could squeeze out of the supercomputer. We got the highest efficiency ever in the biggest supercomputer in the world. Like, we had the most intensive computation ever run, and it was all.
Did the lights turn off?
No, they consume a lot of energy, but I think they figured out how to provide it. So, right.
I imagine the lights flickering and everyone.
Right. So that was a very nice collaboration with Oak Ridge.
Yeah.
And that was in particular tensor network computation, and it really pushed the classical computation to the limit. So it is really a nice target to improve classical computation. The target being fighting any claim on the quantum computer side, but it's really something that pushes classical computation beyond. And classical computation has been, so reliable for decades. We use it all the time to solve any kind of problem. So of course, any improvement there, beyond hardware improvement, but actually on the methods, is.
I mean, we see the
it
biggest
has a potential,
explosion.
Very large impact.
We see the biggest explosion in its usage today with new language models.
Yeah, everyone's using Gemini and ChatGPT all the time. Yeah,
exactly. And and to power those, we need better classical computers.
Yes, and more efficient techniques. Yeah. So it forces us to think.
How do you see the intersection of those two worlds, AI and quantum? I mean, since it's also called Google Quantum AI.
The original vision for the team was, Google is obviously a big part of the development in AI, machine learning techniques, and the whole environment. And so the original interest, as I understand it, before I was affiliated with the team, was to see what was there in quantum computation, right? When the experiments were still small, people were starting to ramp up. And is there anything interesting in the field of AI coming from quantum computing? And so historically, the team has that name. Obviously, the main problem was identify that we need to build a quantum computer and see what we can do with it. And so the interface is very large, right? In many ways. We use AI, but everybody uses,
But do you
Gemini
have some special
similar.
versions of AI you use, or are you also constrained like all the others too?
No, we use machine learning techniques all over the place. In the lab, I'm sure it's used in many ways. We all have, we're research scientists mostly. There's a lot of professional software engineers. I'm a research scientist. I use it all the time to help me code something, improve my numerics, etc. People are exploring if quantum circuits are going to be a good kind of ansatz for machine learning models, for AI models. For learning tasks, there's some proven bounds and some proven guarantees that you can do better once you have a quantum computer, learning some information from a system, from a quantum system, than with classical techniques. So definitely the two fields are not fully separate, right? They have a large overlap. And eventually, maybe we see AI enhanced by quantum computers. I don't know in what form exactly. And again, one of the hard things of thinking about future applications right now is that you're just predicting things, and you're relying on having very good math skills to try to figure out some applications.
And traditionally, we are not that good in this. More oftentimes, we stumble upon something by chance.
Exactly, and it'll be. The AI field was all developed just trying things, and they kind of work.
Yeah.
And we were talking earlier about these heuristics, right? That work.
Yeah.
And so once you have a very large quantum computer, I'm sure so many people are going to have so many ideas to try, and a few of them will work.
So it's a big research field, and for maybe new students, it's maybe highly relevant to join. Is it the right
join what exactly?
To join quantum and contribute and I don't know, join any research facility or try to study more physics or join their labs.
I think
communities.
Eventually, quantum computing, I think it's already starting. I don't know to what level, but it will become a part of the curriculum of people that studying STEM.
Yeah.
And so for people with that interest, I think it's definitely something that the earlier you get into, the better.
And maybe it's also a very interesting hedge against AI, right? If AI needs more data, and as a human you can contribute towards creating more knowledge in the field of quantum, it's a nice symbiotic relationship where you are not at risk maybe of losing your occupation the next
I see.
year.
Yes. Yeah. The more skills you have, the
Yeah.
better, and that's always the case, right? The more cutting edge skills you
Yeah.
have, the more valued you are
Yeah.
in the workforce.
Yeah.
That's a universal principle.
Yeah.
And
And would you describe quantum as the new frontier then?
it's one of them. Yes.
Yeah.
Yeah. Information, quantum computation is definitely at the frontier. It's something that is still a very open research field, very much open, but with large investment and with large promises, and definitely with an accelerating progress that will get something somewhere. It's already gotten somewhere non-trivial in the last few years, and it will get somewhere, much beyond that very quickly. So I think it's the definition of cutting edge field. Yes. It's the definition of the intersection between fundamental research and applications and business, all together, and that's propelling it. At some point in a few years, we'll see.
What are some of the
things.
milestones for this future people should watch out for? If someone claims, or what if I want to keep up, but I'm maybe not in the workforce right now, to join a quantum company or to retrain myself, but I still want to keep an eye out and be informed. What would be some of the signals or milestones I should track?
Yeah. So I think you asked two questions two things in one question. So in terms of joining the quantum computing research, for good or for bad, it's a specialized field. So you have to learn, and you have to read papers and get used to the concepts, and maybe start contributing in some field, and then catch the eye of the big research labs, or maybe start somewhere smaller, more academic, and eventually reach one of the places that is, more that has a more focused target on building a quantum computer, things like that. And so there's many ways to get there, but definitely it all involves a lot of studying, a lot of investigating on your own, and starting
and curiosity
to do research
probably.
and curiosity, of course. But then if you're just curious, or if you're in that process of getting there, and you're driven by this curiosity, definitely the popular media is trying to talk about the field, and it's advertise it, and they do as good a job as possible in trying to reach out to everybody, explaining concepts that are sometimes not intuitive.
Yeah, they are super counterintuitive.
Right, super counterintuitive. And so, but sometimes that's at the sacrifice of precision.
Yeah.
Or sometimes they are hyped, right? Like at some point, I don't know, there's always some fight in between the scientists and the people just try to hype stuff up. And so at some point a few years ago, it was number of qubits. So like, whatever company has 2,000 qubits, and we only have 40, whatever. And then I think now it's kind of more in the...
Is that a benchmark? Would you say this is a relevant thing to watch out?
No, that was a problem, right? That was my point. That at some point there was a misleading benchmark. And then you do nothing with 2,000 qubits if you're going to control them. It's better.
So just claiming you have more doesn't help.
Right, and the way you kind of understand that is reading more technical material. Maybe not the source paper, because it's very technical, but sometimes researchers write like a review paper analyzing where the community is at, and that's written in more plain English, right? In fewer equations and telling you exactly what's the important points, what are the not unimportant points, etc. And so going beyond just reading an article, maybe at the New York Times, that might be exciting, or some other newspaper or on TV, that is really cool that they report on it, and it's kind of on everybody's minds that this is a field that exists and is very exciting. But to start understanding the subtleties, you have to go to the next level. And once you start getting more informed in the field, maybe it's easier to go down to the details and start seeing what's the actual math behind it, what is the actual physics, the applications for what problems and why, etc. So going to deeper levels definitely lets you have a better informed opinion on this.
And any particular sources, or do you think that AI can help someone taking a research paper, put it into Gemini, and then get a summary, for example.
Yeah. It's very, very surprisingly, it's getting better and better by the month, and it helps me understand papers for sure. There is great YouTube channels of people explaining concepts. There's whole courses that go to more or less detail. There's great blogs about it. Some researchers have personal blogs where they explain some ideas in very intuitive ways. It just takes time and effort, right, to find the right resources. But there is resources there at every level. It's just, as everything, to learn it and to get a feel for the environment, it takes time.
And as the final closing question, I would more on a opinion level. This is actually not the last question, but just to get your opinion. Are you more optimistic about the building aspect of quantum, or is it more like a cautiousness towards the risk quantum brings to the table, especially for security? And because there's these two sides of the medal, right?
Yeah.
One side is we could potentially build fascinating new things in the fields of pharma or AI or wherever necessary with a quantum computer. But there's also this big risk. What if someone uses this to break into my bank account or break into my smart locket at my house or take over some national security targets, etc.
That's a very philosophical question.
Yeah.
I think it applies not only to quantum computing but all of technology, right? And if you are a pragmatic person, I think you realize that you might worry, you might not worry, but things happen. Like either you do it or someone else does it, and it's gonna keep happening. And so the only view you can take is pragmatic and be prepared. And take the good things and shield yourself from the bad ones. And so I think if you believe technology is good for humanity, I'm optimistic on it. If you prefer to technology messes up, it brings more, mental health issues, whatever, like it brings us out of our natural environment, then no. But besides that philosophical question, I think it's fine. I think every new technological advancement has brought problems and has brought solutions. And all of them needed some time to absorb and adapt for everybody to adapt to them. When the train came up, I think people thought it might cause health problems going at such speeds or things like that. And then, nothing happens. Life expectancy keeps going up. So it will bring challenges for sure. And so it's the job of everybody to prepare for that. But it will bring solutions to open problems that humanity would like to solve. So I'm not especially worried, I guess, because that happens every time there's something new. But there's definitely, everybody has to keep an eye open for what it will bring.
And the road towards the next 5-10 years, if I understand the position you're coming from, is more from an alignment of the stock and doing these small wins every few milestones, every few months. But the key insight I had from this conversation is once you read a specific hardware requirement, there are already so many prepared applications and physical theorems and algorithms waiting to be tested out or waiting to be used by a sufficient quantum computer.
Yeah. There is definitely things waiting at the very end.
So we are not saying, hey, once we get the quantum computer, then we are going to think about how to use it.
No, everything is happening simultaneously.
Everything.
It will be a waste of time.
Do you think that the elaborate or the amount of work is balanced, or do we have more on the side of even the theoretical? I mean, from here on this conference, I get the impression that we have way more theoretical work than I ever assumed.
No, you can argue for both. You can argue that, okay, if we don't have error-corrected quantum computers yet, or not at a large scale, why are we thinking so much of algorithms? Or you could argue, this an extremely large investment from different countries to get to an error-corrected quantum computer. How come we're not thinking more about algorithms to actually, have return on that investment? So I don't think any field is overdoing it. And the implementation side, the actual building a quantum computer, the experimental side, is so challenging that it's going to take a few years. And so it's a great window to explore as much as we can before we have something, and with the tools we have now, which is mostly small devices and math. So I don't know which one is like falling behind. It's usually caught up pretty quickly. Like if that's the nice thing about developing everything in parallel, that you see weaknesses everywhere, and they might need more presence there, or more researchers see the chance to contribute there.
And do you think everything is well coordinated as it is right now, or can we improve somewhere?
I'm sure it can improve, but there's a large effort in coordinating. That's one of the nice things about the fact that industry got in the field, because the field was a field of research that was mostly in universities, national labs, research institutions.
Yeah.
And the natural thing to do there is to have small research groups that are very focused on some topic, and they publish papers that relevant to their community, and it's really hard to put everybody together. And so these large efforts, mostly coming from industry, at least in the West, they put together tens or hundreds of people working under one command to have one mission. And so then you have an incentive to coordinate everybody. And the places that have been successful in the recent years have been the ones that have solved that problem, that sociological problem, the best, right? That they could actually coordinate and decide quickly, this is not a good idea, etc., instead of having one professor that is a specialist on some technique, and they're just going to go down that route. As a corporation, as a big group in a corporation, you can take better decisions. You have different expertise, fields of expertise. And definitely coordination is crucial.
And within your team, you have a right mix, as you said, of multidisciplinary people.
Yeah, and different holes keep appearing, right? And some people are hired, or eventually it will be the opposite. Eventually, the physics is so well known, the engineering is so developed, that you don't have to do research on some things. They are already, beyond good enough.
Yeah.
So,
but the research will keep on going. There will be always new
features. And of course, and we have great classical computers, and there's a lot of research on computer science. Yeah,
of course.
Yeah, so research will never stop. Just the pressing issues will change.
Yeah,
they'll appear and they'll disappear. Yeah, and that needs coordination. Yeah, that needs a group dynamics to adapt and sit on the different fields that need more attention.
And some final thoughts from yourself, what you would give someone who is just starting out his journey in quantum, or is even like fairly advanced? What would you say, like from your personal experience, you would recommend?
So at the personal level, it's important to understand if you like more fundamental research, or if you get excited about being part of a maybe much larger group, but that has the funds and the technology to get somewhere more quickly. And so that kind of informs, if you want to do research in this field, your decision of whether you want to go down become a professor and have a few students and contribute in some very specific field, or you want to be part of an effort that has experiments and people work on algorithms and error correction and many other things, and people from other backgrounds, software engineers and material engineers and everything. So that's important to understand. And once you make a decision, or you are closer to making a decision on what path you want to take, although sometimes these two things overlap. There is, professors that are entrepreneurs and they have their startup, or that they collaborate with massive groups, so they kind of create their organization, even if it's not officially called like that. Or people in our team or in other companies that do research and they have a lot of freedom and they really come up with fundamental results. So it's not exclusive, but it's kind of one tends one way, the other one tends the other way.
But the fundamental decision to join quantum, would you advise for that?
For that?
Would you advise someone primarily to go into the quantum field?
It's a very exciting field. Yeah. So if you like research, but you also like there's research that is very removed from application. And there's research that is extreme, that you can apply tomorrow. And so this is in between, getting closer to the second. And so if you like that, if you like a fast fast-paced research field, but still research with a lot of open problems, some fundamental problems, and very diverse set of skills, then it's the right skill, the right field. And if you are excited about possible applications, like this has promises on some applications, and it's very interesting. It's the first time we're moving away from the computers we used for getting close to a century.
Yeah.
Right? From the same paradigm of computers, and for the first time we're walking away from that. And so I think it is a very interesting revolution in a way.
Mm-hmm.
And
so it opens so much food for thought. For me
so
personally,
much food for thought.
When we talk about these concepts, it always keeps me thinking about, for example, what is time actually, right? If we can run something in a quantum computer which would take trillions of years or billions of years. This time dilution or the time difference within that, and it's basically part of our world, but it's still kind of accelerating it to something unimaginable even.
As you know, as a cryptographer, time is a very important thing to consider. It might be what protects you from decrypting something.
Yeah.
I think this one out again.
Yeah, this is.
Do you want to change it and finish it? Okay.
Let's do it like this. I just have to touch. The thing is, if I don't touch it,
that's fine.
I cannot figure out how to get it to not go into this mode.
Yeah.
So that's a product from Apple, obviously.
As I was saying, as a cryptographer, you know that time is a very important parameter, right? And it's fundamental to your assumptions for what is secure and what is not.
Yeah.
And so this field, if quantum computers deliver, that changes a lot of things. Yeah. It changes a lot of things. It changes how you think about that one parameter for sure.
Yeah. No, but people never had, since we had the biggest shock for, let's say, understanding of time for me was relativity, right? So if you speed something up super quickly, time gets diluted, right? That would be something very like time for us is a constant, right? As humans here, and then
as a daily application.
Exactly.
Every daily experience is we don't play too much with time, but this would.
Exactly.
This would change our vision for sure.
Exactly, and that is something which fascinates me every day. It's
right.
Like,
in the context of algorithms, it would really change that.
Yeah. So this is really, really cool. Thank you so much for joining.
Yeah, thanks a lot for inviting.
I hope you had a great time.
I had a great time. Yeah.
I mean, I could talk to you. You're very, very well versatile in every field of quantum. I think this could also go on for like 5 hours.
Yeah, I enjoyed it a lot. Yeah, I love talking about this. So thanks. Thanks. It was very fun.
Thank you so much for being
Thank
here.
you.
And thank you so much.